Hey, this is Horner. We're going to look at section 10.1, the basic energy model. We know that models in nature, typically what we'll do is we'll look at the systems within it, and if we circle the system that we have here, we say that all of the energy is inside the system. So that's what we're going to look at. The total energy is basically just the sum of all the energies that you see, and there's a lot of different types of energies that we're going to talk about. Anything outside of the system means that we're putting energy into or doing work on the system, and any energy that comes out means that the system is doing work on something else. So we'll look at those things here in a little while. Different types of energies. The first type of energy is kinetic energy or energy of motion. Second type is called gravitational potential energy, and that's just any energy that comes from being off the ground. So you're at a certain height off the ground. So motion, certain height off the ground. Elastic or spring potential energy. So this is when you have a spring or other elastic object like a rubber band. Thermal energy is all of the kinetic and potential energies of all the molecules in an object. Chemical energy, that's energy stored in bonds. And finally, nuclear energy, which is stored in the mass of the nucleus of an atom. So those are the different types of energies. We won't do all of those and use all of them all the time, but we just want to make sure that you are aware of the different types. Energy transformations, we can transform energy from one type to another. So you'll notice that we can go from kinetic to potential, and from potential to chemical, from chemical to, and you'll notice this is ETH, and this is thermal energy. Notice that most of the arrows do go back and forth, so from K to U, U to K, K to E, E to U, but the ones that come from potential to thermal, kinetic to thermal, and chemical to thermal don't go back the other way. So we'll talk about why in a little bit more time. But we do want to make sure that you see that energy can be transformed from one type to the other, and that's energy transformations. The weightlifter here is taking all our chemical energy and putting it into gravitational potential by lifting it up above her head. The diver here on the springboard converting all of the potential energy into kinetic energy. As that diver rises, the kinetic energy is transferred into a gravitational potential again. So lots of different transformations from one to the other. So here's our first quick check. We have a child on a playground swing, motionless at the highest point of his arc. What energy transformation takes place as he swings back down to the lowest point? So if we think about this kid swinging, we're at the lowest point here. If they swung out to here and they stop, the energy here should be all potential energy. And the letter that we'll use for this is U. G, so that's potential energy due to gravity. And then when they swing back down, at this point, they're at the lowest point that we're measuring. So we're going to say that the height here is equal to 0. So at this point, we have maximum speed. If we have maximum speed, that means that we're moving. And so we've gone all the way to kinetic energy. So the only good option that you have here has got to be letter B, going from potential to kinetic energy. And if we check, that is the correct answer. For QuickCheck 10.2, a skier is gliding down a gentle slope at a constant speed. Okay, so here we've got a skier gliding down, so I'm going to do my best with skis. There we go. And this person is going down the hill. That's their scarf, whatever. And as they go down, they don't pick up any more speed. So they don't pick up any more speed. It says constant speed. So our V here, let's just call it 5, and at the bottom our V is also 5. So the question is, they do have potential energy here, and it's got to be transformed into some type of energy, but the speed doesn't pick up at all. So we know that this cannot be kinetic energy. So we cannot use kinetic energy here. What is it that is keeping them from picking up speed? Well, it's got to be friction. And if you rub your hands together, that force of friction will generate thermal energy, or ETH. So when we look at the answer here, you'll notice that we're going from potential energy due to gravity to thermal energy. And that is the transformation that's taking place. So be careful, just because you're going from somewhere up high down to somewhere low does not necessarily mean that you are picking up kinetic energy, only if you pick up speed. The next one is talking about energy transfers and work. So as we said before, if you have something working within a system, so we're transferring energy from kinetic to potential, potential to chemical, chemical back to kinetic. If any of that energy goes out of the system, okay, if energy is transferred from the system to the environment, that typically happens as heat. And that's usually what you'll see. Energy can also be transferred from the environment to the system, and that's usually work. Now, that doesn't mean that you can't have heat being pushed into a system or work coming out of a system. You sure can. But that's essentially the breakdown in between that system barrier and the environment. So if I'm going from the environment to the system or system and environment, I'm either doing work or generating work, or we're expelling or taking in heat, one of the two. So work basically is just defined as mechanical transfer of energy to or from, and heat is non-mechanical energy being transferred to or from the environment. For the next slide, this is some good examples of work and energy. So the athlete does work on the shot, okay, gives it kinetic energy. When you strike a match, your hand is doing work on the match, giving it thermal energy. So that makes that flame light up. And then before this boy shoots you right in between the eyes here with this slingshot, the boy does work on the slingshot, giving it elastic potential energy. Now, elastic potential energy is transferred to kinetic energy in the motion of that little shot that's coming out. QuickCheck 10.3, so we have a tow rope pulling a skier up a hill at a constant speed. So here's our hill, here's the little pulley for the tow rope, and then here you are, and your skis are under your feet, and you're moving up the hill. But you're doing so at a constant speed. So here your speed is constant. And because your speed is constant, you don't have any change in kinetic energy. They want to know what energy transfer or transfers are taking place. So are we doing work and creating potential energy? Are we doing work and creating kinetic energy? Are we doing work and creating thermal energy? Is it A and B, or is it A and C? And if we think about this, because we're not changing speed, we can't choose letter B. So this is only going to be answers A. So here we're picking up height, and because we pick up height, there's a change in height. There's got to be potential energy. And then because we don't change speed, it can't be kinetic. But if we are doing something, getting some work, there's got to be a little bit of heat loss here. So ETH is what we're making. So that is both A and C. For the next thing, this is the work and energy equation. So work represents energy that's transferred either into or out of a system. And the total energy of that system changes by the amount of work done on it. So we'll notice that the change in energy is equal to the change in kinetic, change in potential due to gravity, change in potential, you get it. And all of that is equal to the work. And so work can increase or decrease the energy of the system. And if no energy is transferred into or out of a system, we say that it's isolated. It's all by itself. And you won't have any work or heat going into or out of that system. QuickCheck 10.4, a crane lowers a girder into place at a constant speed. So here there is no change in kinetic. Consider the work done by gravity and the work WT done by the tension in the cable. They want to know which one is true. So the work done by gravity is either greater than or less than zero. Same thing with the work due to the tension. And if we go to the answer, we can talk about the reasoning here. We know the work of gravity has got to be greater than zero, and the work due to tension has got to be less than zero. So the downward force of gravity is in the direction of motion. So we're going to say that that is positive work. So because we're trying to lower this girder, we're trying to go in this direction, and we know the potential energy due to gravity is going in that direction. And how do we know that? Because we can do a free body diagram on the beam. And so this would be weight, which is equal to mg. And so we know that that is the force due to gravity. And then we have a force of tension, and that force of tension is up. And so because we're moving in this direction, we know that the work due to gravity is got to be positive because it's in the downward and the same direction of motion. And then the work done by tension is up, so it's got to be negative. So this one's negative and that one's positive. And that's kind of how you deal with the direction of work. 10.5, Robert pushes the box to the left at a constant speed. What kind of work does he do on the box? And so for this one, we know he does positive work because he's moving it in this direction. So his work is going in this direction. He's trying to get it to move in that direction. So that would be positive work. That would be positive work. The law of conservation of energy here basically just says that all of the energy within a system remains constant. Okay. So if I do work on the system or the system does work on something else, we're not looking at it, we're just looking at what is totally inside of that system. And that is the law of conservation of energy. The next section we'll talk about, and I know we've already talked about a little bit, is work.